This topic is called finding the volume of an irregular solid, and this is going to be the disk method to start off, and then we're going to go to the washer method. So let's start with the disk method. Basically, I want you to imagine a curve, and let's talk about this green curve. And then I want you to think about a coin or a disk, and the size of that disk is going to be the radius will be the height from the curve all the way down to the x-axis. And so then you would rotate that cylinder or that coin or that disc all the way around the x-axis. Okay, now you're going to do that an infinite number of times, and you can think about right here how your coin would be a lot smaller, right? You'd have some sort of a cylinder that would be going around here. I think I made that too big. Something like that, and then it's coming back up the other side. Okay, so you've got an infinite number of those disks from -3 to 3. So can you in your head kind of envision what that would look like? How about these? Could you imagine revolving these around the x-axis? So we would get something like this. What would this be if I revolve this around the x-axis? Well, if you said a cone, something like this, you are correct. What about this? What would this one be if you were to take this and rotate it around? Well, it would actually be a pretty large cylinder. Right? You'd be getting this cylinder that would be wrapped around the x-axis. Now, how about wrapping the semicircle around the x-axis? Well, you would actually get a sphere. Okay, think about that sphere, how you'd be creating that 3D revolution. What about if I was creating it over the y-axis? Well, obviously that would look a little bit different. It'd be going over here. Okay, it'd almost look like you had like a little bowl here. Okay, think about kind of like a empty bowl inside there. All right, now let's go ahead and actually try to solve one of these problems. So let's say that we have a rocket company that wants you to build a nose cone in this shape. Okay, it's got square root of x. So you put a piece of wood in a lathe and you're going to turn it into a shape to match the above curve. And you're going to rotate it around the x-axis and you'll see how you would get that. And if you don't believe me, you kind of have something like this, and it would be rotated around there. And so the question is, what is the volume of that shape that we have that rocket company wants us to create? Well, let's talk about what the formula would be. So one way to think about it would be to cut it into a series of thin, flat cylinders, which we call disks, right? Remember, this is the disk method. So we have an infinite number of those. Right, you could think about keep drawing them in here. There's a smaller one right there. There's one right there. There's one right there. There's an infinite number of these. And we call the thickness of these dx because there's an infinitesimally amount of those. They're infinitesimally small. And we talked about that a little bit earlier. Now, A of x would represent the area of one of these disks. Oh, I'm getting really good at guessing where those arrows go. And so the volume would be pi r squared for one of the flat cylinders, and then we would want to add up the area of all of those, or the volume of all of those cylinders. And that's where that integration comes in. And so what we're doing is we are summing the areas, the area of this disk, and this right here represents the width. So we all should know that the area times the width gives us, this actually represents volume. So we're summing up all the volumes of all the disks. And to get that volume, we're doing the area of the circle times the width of that circle, that disk, if you will. So that's why the formula is what it is. And we're going to talk about why the radius would be the square root of x. And maybe it's not super obvious here, but if you were to look at our graph being the square root of x, notice that the radius of this disk is the function the square root of x. So that's why we would have r being the square root of x. So here's the formula that I would like you to write down. You certainly could write down the other one, but we have that the integral from a to b of pi r squared dx is going to give us the volume of our revolved curve. So please get this down. And I've already made a hint at it, but your radius is going to be your function in terms of x. And the reason why is we're revolving it around the x-axis. Okay, and obviously this is a dx because we are revolving it around the x-axis. So I'd like to actually complete this problem. So this is going to be the integral from 0 to 4, remember that's what we're revolving, of pi r squared dx. Remember my radius is this, it's the square root of x. That's the square root of x. You can think of that as being a y distance, and we know our y distance is the square root of x. But don't overthink it, it's just the equation. All right, so I'm going to go ahead and solve this. I'm going to pull my pi out. I'm going to have from 0 to 4. I know that the square root of x quantity squared undoes itself, and it's just giving me x dx. So now I find the integral. That's going to give me a pi x squared over 2 from 0 to 4. Okay, so plugging in 4 first, I get 16 pi over 2, which is 8 pi. And then I also get a minus 0. So the volume of this is going to be 8 pi units cubed, because we're talking about volume. And don't forget, we are summing up the area of a disk times its width, and we know area times width gives us volume. So that's why that formula works. All right, the next thing that we're going to talk about is finding the volume of an irregular solid using the washer method, and we're going to just revolve around the x-axis. Now for this method, we actually have a top curve and a bottom curve, which creates this kind of, intersection area. And so your radius of your washer, a washer looks like this right here with the hole in it. So you've got your radius of it being the top curve, and then you would kind of subtract out that bottom area. And so you can kind of visualize this yourself, but let's talk about kind of how we would approach problems like these. So here's the formula right here, and I want you to get that down. Basically what we have is, sorry about that, we have two circles. And if you don't believe me, let's go ahead and take a look at this right here. You can rewrite this, and please don't, let's just imagine it as being a pi r squared minus a pi lowercase r squared dx. Notice how all I did was distribute the pi. But basically it's saying take the area of the big circle minus the area of the small circle. And so here we go. Here's my big circle right here. It would be the whole gosh darn thing. So that's the area of your first, and that would obviously be a radius of your top curve. Minus, that minus comes from subtracting out that kind of inner circle right here. And that's how that works. So that's your formula for the washer method. Now let's do example 1 of the washer method. So for here, I have to identify my bigger radius. Oy vey. My bigger radius is going to be this, the one that's taller. So I'm going to have pi from 0 to 1 of my bigger radius, which is going to be an x squared, minus, what's my smaller radius? Well, that would be an x cubed squared dx. Okay, and at this point, I'm just going to pick up my calculator and I'm going to find that. I get 0.19 units cubed. So again, what we are doing is we're identifying our bigger radius, or the radius of our big circle, and that's going to be my x, and don't forget to square it. And then same thing here, my inner radius, which is the one of the hole, the thing with the cutout, what we're subtracting out, we have that right here, and then we square that as well. All right, so let's go ahead and try this one. We're going to again rotate this one around the x-axis. So here we would have the integral from 1 to, I wonder where that intersection point is. I'm going to pick up my calculator right now, graph those two things, and I'm going to make sure that my intersection point is what I think it is. I think it's at 2, but it might be a little bit less than that. Well, I just confirmed it on my calculator. It is 1 to 2 here. I'm having a real hard time with this thing not wiggling. All right, so now I'm going to put my pi on the outside. Now here I'm going to have my uppercase R squared minus my lowercase r squared. And my uppercase R always stands for that bigger radius, or the top radius. In this case, that's going to be the square root of x minus 1. Okay, and my inner radius, the thing that I'm going to subtract because it's not going to be a part of my volume, will be this x minus 1 squared dx. You can certainly simplify this if you want before you put it in your calculator. For example, the squared and the square root will cancel out, but you're just going to go ahead and plug that into your calculator. And why don't you confirm that you get the same answer as me? I get a 0.94247, and again, that's going to be units cubed. Now, after doing this, I think I forgot to multiply the pi back in through here. I did put it right there, but I needed to take my 0.19 and multiply it by pi, and instead I get a 0.598. I would redo this video, but we're 12 minutes in, and that's just not going to happen. All right, last problem we're going to do together. This is going to look more like your practice in class. So for each problem, find the volume of the solid that results when the region enclosed by the curves is revolved around the x-axis. So we have to draw a picture first. Okay, my y equals negative x squared plus 3 is actually going to be a sad face parabola right there. My y equals 2, I'm just going to make sure you know that this is red. My y equals 2 is going to look like this. Just kidding. It's going to look like this. I made that silly mistake. Y equals 2, because remember, y's are horizontal. And then x equals 1 is going to look like straight up and down at x equals 1. And then x equals 0 is going to be this right here. So we're really talking about this area right here being revolved around the x-axis. Now, it's always a good idea to graph this on your graphing calculator to make sure that you've done this right. And you might tell that actually this purple line right here, that x equals 1, goes through right here. And there's no way to really know that unless you do some serious math or do it on your graphing calculator. All right, so there's what we have. We're revolving that around the x-axis. So this is going to be equal to pi uppercase R. Well, our uppercase R comes from here, which would be this function, which is going to be a negative x squared plus 3. Don't forget to square it. Minus, now I need my smaller radius, which is actually going to be 2. Kind of weird, but it looks like this. Dx, and we're going from 0 to 1. This is my 0 to my 1. All right, picking up my calculator, I get a 10.05 3 units cubed, because again, we're talking about volume. So as a reminder, we always put our pi, we take our bigger radius, we square it, minus our smaller radius, we square it. And the reason we do so is because we're trying to subtract that inner part of our washer. All right, thanks for watching. I know it was a long one. Bye now.